Hello everyone, this is Kalpana here. In this video, we're going to see a problem from partial differential equations using eliminating the arbitrary constants. So let's get going. Problem. Form the partial differential equation by eliminating the arbitrary constants a and b from x minus a whole square plus y minus b whole square plus z square equal to 1. Here a and b are arbitrary constants, right? So here we are given a differential, not differential equation, it's a relation. We are given a relation x minus a whole square plus y minus b whole square plus z square equal to 1. Consider it as equation 1. We are asked to find or form a partial differential equation by eliminating this a and b arbitrary constants from this relation. So now what we are going to do is we'll just partially differentiate one with respect to x and one with respect to y. So let's see that. Partially differentiating one with respect to x. Dou by dou x of okay, simply partially differentiating on both sides with respect to with respect to x, sorry. So now we can write this as dou by dou x of the first term x minus a whole square plus dou by dou x of the second term. It's not necessary to write these two steps, okay, we can just go directly. Dou by dou x of z square equal to partial derivative of a constant with respect to x is 0, okay, is equals to, here we are partially differentiating the terms with respect to x, so y will be treated as constant and here a and b are arbitrary constants, okay, and z is a function of x and y. Fine, now partial derivative of x minus a whole square with respect to x is 2 times x minus a into the inner derivative, that is partial derivative of x minus a plus partial derivative of y minus b whole square with respect to x is 0 because y and b are considered as constants here, right? So it is 0 plus partial derivative of z square with respect to x is 2z into dou z by dou x equal to 0, okay. This gives us 2 times x minus a into partial derivative of x with respect to x minus partial derivative of constant a with respect to x plus 2z into dou z by dou x equal to 0. This gives us 2 times x minus a into partial derivative of x with respect to x is 1 minus partial derivative of a constant with respect to x is 0 plus 2z into, since we have a notation, p equal to dou z by dou x. So just replace dou z by dou x by this p, you'll get 2zp, right? Then this becomes 2 times x minus a into 1, which gives 2 times x minus a plus 2 times zp equal to 0, right? Or we can write this as 2 times x minus a equal to minus 2 zp. Here 2 gets cancelled, otherwise you can just take 2 to RHS, then 2 gets cancelled. Then you'll get x minus a equal to minus zp. Therefore, x minus a equal to minus zp, consider it as equation number 2, okay. Fine. Now let's partially differentiate one with respect to y. Okay, instead of writing too many steps, we can just directly partially differentiate 2 with respect to x. I'll show that also. Okay, partially differentiating 1 with respect to x. 2 times x minus a into inner derivative. Partial derivative of x with respect to x is 1 minus partial derivative of constant with respect to x is 0, right? So you'll get 1 minus 0, which is 1. So you'll get into 1 here. Plus partial derivative of a constant with respect to x is 0. Plus partial derivative of z square is 2z into dou z by dou x equal to partial derivative of 1 with respect to x is 0. Since 1 is a constant, right? You'll get directly 2 times x minus a plus 2z into, since we have a notation p, just replace it by p. Now take the second term to RHS. Take these 2 to RHS. From this you'll get x minus a equal to minus zp, which is our equation 2. Okay, but many people gets confused how to find partial derivative of x minus a whole square, y minus b whole square and z square. So that in order to clear that, I'm writing too many steps. Okay, you can just skip those steps and do like this. Just skip the steps that can be avoided. Okay, now partially differentiating one with respect to y. Okay, I'll go for the direct steps now. Partially differentiating with respect to y, which says that x is constant and here z is a function of x and y. Okay, so partial derivative of a constant with respect to y is 0 plus partial derivative of y minus b whole square gives 2 times y minus b into inner derivative with respect to y. Partial derivative of y with respect to y is 1 minus partial derivative of a constant with respect to y is 0. So 1 minus 0 gives 1. We'll get 1 here plus partial derivative of z square with respect to y is 2z into dou z by dou y equal to partial derivative of a constant with respect to y is 0. This gives us 2 times y minus b plus 2z into, since dou z by dou y equal to q, so we'll get q equal to 0. Now take the second term to RHS. Now take this 2 to RHS. Where 2 gets cancelled and you'll get y minus b equal to minus zq. Therefore, y minus b equal to minus zq. Consider it as some equation number 3. Now, again I'll partially differentiate 1 with respect to y in depth. Okay, let's see that also. Dou by dou y of the LHS part dou by dou y of RHS part. This gives us, here we need to partially differentiate with respect to y, so this term is constant and z is a function of x and y, and here we have the variable y, so we'll partially differentiate this with respect to y and this with respect to y. Let's see. Dou by dou y of first term plus dou by dou y of second term plus dou by dou y of third term equal to partial differentiation. Partial derivative of 1 with respect to y is 0. This gives us partial derivative of a constant with respect to y is 0 plus partial derivative of y minus b whole square with respect to y is 2 times y minus b into partial derivative of the inner function y minus b plus partial derivative of z square with respect to y is 2z into dou z by dou y equal to 0. This gives us 2 times y minus b into partial derivative of y with respect to y minus partial derivative of a constant with respect to y plus 2z into, since we have a notation dou z by dou y equal to q, just replace dou z by dou y with q. Okay, this gives us 2 times y minus b into partial derivative of y with respect to y is 1 minus partial derivative of a constant with respect to y is 0 plus 2zq equal to 0. Right, from this we'll get 2 times y minus b, 1 minus 0 is 1, right? So we'll get obviously 2 times y minus b plus 2zq equal to 0, right? Now take the RHS part to take the second term to RHS, you'll get 2 times y minus b equal to minus 2zq. Now take this 2 to RHS, you'll get y minus b equal to minus 2zq by 2, where 2 gets cancelled. Then y minus b equal to minus zq. Therefore, y minus b equal to minus zq is our equation 3, right? Fine, now we got x minus a equal to minus zq, which is equation 2, y minus b equal to minus zq, which is equation 3. Now by substituting 2 and 3 in 1, we'll get the required partial differential equation. Okay, by substituting 2 and 3, the arbitrary constants gets eliminated. Okay, then that results to an equation of the form sum f of x, y, z, p, q equal to 0, which is the required partial differential equation. So let's see that. We have equation 2, x minus a equal to minus zp and y minus b equal to minus zq, which is equation 3. Now substitute 2 and 3 in 1. We have 1 x minus a whole square plus y minus b whole square plus z square equal to 1. Now replace x minus a by minus zp, you'll get minus zp whole square plus replace y minus b by minus zq, you'll get minus zq whole square plus z square equal to 1, which gives us z square p square plus z square q square plus z square equal to 1. If you notice, we are having z square in all the 3 terms of LHS, so let's take it common. You'll get z square times p square plus q square plus 1 equal to 1, right? See, we don't have any constants a or b here, so this will be our partial differential equation. Therefore, z square into p square plus q square plus 1 equal to 0 is the required partial differential equation. Well, we have seen a problem from partial differential equation in this video. I hope you'll understand. We'll see you in the next video. Until then, bye bye.